Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the fundamental theorem of calculus, which basically enables us the connection between the two important parts of calculus, differential calculus and integral calculus. So the fundamental theorem of calculus is appropriately named because it established the connection between the two important parts of calculus, differential calculus and integral calculus. So even though they are like really different approaches, what we are doing in these two parts of the calculus, in one we are finding the slopes of the tangent lines to the curves, and we've learned that they are superbly useful in many different applications. And in integral calculus we are interested to find the areas under the functions. So throughout this course we're going to see that it is also important for us, and we can apply this into the many different areas in order to get the really useful information out of this. So the Newton's mentor at Cambridge, Isaac Barrow, discovered that these two problems are actually closely related. In fact, he realized that differentiation and integration are inverse processes. So later on, Newton and Leibniz, who exploited this relationship, put the calculus into the elegant mathematical method. So they saw that a fundamental theorem enables to compute areas and integrals very much easily without doing any calculations of the limits of the sums as we did before in order to evaluate the integrals. So let's learn what is the fundamental theorem of calculus. So we're going to split this into the two parts. The first part is going to be about this kind of functions. So the big f of x is going to be the integral function. So essentially we are going to integrate some function small f of t with respect to the t from some constant which is fixed. So this constant is going to be fixed until some variable x. So essentially the argument of the f is not here inside the integral. It is on the border. So essentially, geometrically, it means that I'm going to choose the ending point of the interval until which I'm going to integrate my function. So essentially, this area corresponds to the integration of this curve. So let's assume that this curve is given as the f of x, or f of t in this case, right? So f of t, so this is the t and this is the y, let's say. Then its integration with respect to the t from a to the x is going to give me this area. So what I want is I would like to express this area as the function where I'm going to move the ending point of this area. So the ending point of this area is going to be my variable now. Okay? So let's try to reveal its properties and try to understand what type of the function it is. So in order to do this, let's evaluate the areas under this curve. So essentially, let's define this function, capital F of x, which is given as the integration of another function from a until the x for the following curve. So I'm going to basically define the big capital F of 1, of 2, of 4, of 6, of 9. So let's evaluate the f of 2 here. So what does it mean? The f of 2 is essentially the area under this curve, under this blue curve, so under this blue curve, which is f of t in our case. So from 0 to the 2. So you can see here that this is triangle, and if you would like to find the area of the triangle, we have to multiply the width of the triangle, which is equal to the 2, to the height of the triangle, which is equal to the 3, and divide this to the 2, which is going to be 3 times the 2 times the 1 over 2, it is going to be equal to the 3. Well, what is the value of the f of 2, or f of 4, sorry? So if I would like to find the value of the f of 4, I have to find the area from the 0 until the 4 under this curve, right? So it is going to be the f of 2, right, the area until the 2, plus the area of this rectangle. And we know how to find the areas of the rectangles, right? So we have to multiply the width of this rectangle, which is equal to the 2, to the height of the rectangle, which is still equal to the 3, which is going to be 6, right? So it is going to be f of 2, which is 3, plus 6, which is going to be 9. So the f of 4, sorry, is equal to the 9. So what is f of 6 now? So if I would like to find the f of 6, I have to find this area. It is going to be the summation of f of 4 plus the area of this triangle now. In order to find the area of this triangle, again, I'm going to multiply the height of this triangle, which is equal to the 3, to the width of the triangle, which is equal to the 2, and divide this to the 2. Again, so the area of this triangle is equal to the 3. And if I add this into the f of 4, it is going to be equal to the 12. Okay, so you see, so the f of 2, if I substitute this 2 as an argument to this function, it is going to give me the area until the 2. If I substitute the 4, it is going to give me the area until 4. If I substitute the 6, it is going to give me the area until 6. Now, if I would like to find this integration until 9, I have to find this area, and I have to subtract this from the f of 6. Because if you remember, the areas under the curve or over the curve, where the curve is under the x-axis, are going to give you the negative values. And if you remember, the integration is net area, not just the area, right? So if you're going to have the curve under the x-axis, it is going to give you the negative value of the area. So this area is going to be the height of this triangle. So the height of this triangle, which is equal to the 2, it seems to be equal to the 2, times the base, which is equal to the 3, right? The base is equal to the 3, divided to the 2, which is going to be equal to the area of this triangle is equal to the 3, but since we are finding this using the integration, it is going to be equal to the minus 3. So the capital F at the 8 is going to be equal to the 9 again, so because I have to subtract the 3 from the 9. So you see, so I'm just moving the ending point without changing the starting point. And by putting different values for the ending point, I'm finding different values of this function, capital F of x. So this function essentially is going to give me the area under the curve up to a certain point x. So this is what is called this integral function. Well, the first part of the fundamental theorem of calculus is connected with this function. So let's assume that you are given this function f of x, where please note that this argument of this function x is not inside the integration, it's on the border of the integration. It means that I have to integrate this up to this point x. It appears if I take the derivative of this function, capital F, with respect to the x, I'm simply getting the function which is inside this integration. So I don't need to even take the derivative. I don't need to do anything. So this function inside the integration is going to be simply the derivative of this capital F with respect to x. So this is called the fundamental theorem of calculus, part 1. So let's do first of all a small exercise, then we are going to try to reveal its applications and try to understand this a little bit more deeper. So let's say we are given now the function, so the capital F of x, where the argument is going to be on the border of this integration. So if you need to find the derivative of this f with respect to the x, so essentially df with respect to the dx, so you don't need to integrate this function first and then take its derivative. So it appears it is just enough for us to simply write this as the 1 plus x in the square only. Because if you note here that our function f of t is equal to the 1 plus t in the square, right? So you can see here the fundamental theorem of calculus, part 1. That if you are going to get f of t inside your integration, the derivative of this function is going to be simply f of x. So essentially, I have to substitute this t and this t with the x in order to find the derivative. This is what is the fundamental theorem of calculus. 1 tells us that sometimes the border of this integration might be a function of the variable. Okay? So although the formula of the form of f of x may seem very strange, we may define this function, so the way of the definition of this function looks like very strange. It is very although the formula how we are using this function, how we are defining this function looks very strange because it is different than the functions which we have defined so far. This kind of definition of the functions is very common in many different areas of science, like in chemistry or in physics or in statistics. For example, in physics, there is so-called Fresnel function, which is used in the diffraction of the light waves, which is recently used in order to design the highways, is defined in this way. So it is going to be the integration of the sine function with respect to the t from 0 until the x. Or, for example, one of the most important functions in probability theory, which is the cumulative standard normal distribution curve, is also defined using this kind of function. So this cumulative standard normal distribution curve, phi of x, is going to define you the probability of your normal distribution up to some point x. It is, again, one of the really important functions in probability theory. So you see, so it is very common to use this kind of functions in some application-based problems as well. So previously, we made an exercise where we needed to evaluate the differentiation of this kind of function, where the border of the integration was simply x. But sometimes it is possible that in the border of the integration, we are going to have the function of the x, not just simply x. So in this case, we've got the function of the x, which is x in the 4. So how to find the derivative of this function in this case? Well, in this case, we're going to use the chain rule, the so-called chain rule. So what we are going to do is, so we have to find the derivative of this function with respect to the x. This is what we have to find. But the problem is, on the border, I don't have simply x. I have x in the power of 4. So it means that if I would take the derivative of this function with respect to the x in the power of 4, I could make this easily, right? Because symbolically, it was x in the power of 4 on the border of the integration, and I'm taking the differentiation, with respect to the x in the power of 4. So I need to look to the x in the power of 4 symbolically. But I can't really just change x into the x in the power of 4 and equalize this. So I need to use so-called chain rule. So I have to multiply this to the dx in the power of 4 with respect to the dx. Okay? So what is going to be the derivative of this function with respect to the x in the power of 4? From 1 to the x in the power of 4 second of t dt times the derivative of the x in the power of 4 with respect to the x. Again, according to the fundamental theorem of calculus 1, you can see here that if you are going to get this x here, and if you're taking the derivative with respect to the x, it is simply f of x. So the same is, so these two variables here are the same. So I don't look, it is not important what is there. So the most important part is that they are the same. Then the derivative is going to be simply equal to the second of x. And I have to multiply this to the derivative of the x in the power of 4 with respect to the x. It is going to be 4x in the cube. So this is how we can take the derivative of this kind of functions with respect to the x if the border of the integration contains not just the x, but the functions of the x. We're going to use so-called chain rule in order to find the derivatives. Well, this is the first part of the fundamental theorem of calculus. We're going to define now the second part, which is also called as the Newton-Leibniz formula. So if f is continuous in some interval between a and b, then the integration of this f from a to the b, it is going to be big F at the b minus big F at the a, where the big F, the capital F, is the antiderivative of the small f. The antiderivative means that if you take the derivative of the capital one, you're going to get the small one. So while usually you're going to given the small one, you have to find its antiderivative. You need to usually guess this, or we've learned about the methods of how to find the antiderivative, or there is a bunch of formulas which help us to find the antiderivatives in general. This is the important part of the fundamental theorem of calculus, which is also called like a fundamental theorem of calculus part 2. Sometimes we call this theorem as the Newton-Leibniz formula. So let's try to do some examples and try to learn how to do this. So let's say we have to evaluate this integration of the e to the power of x from 1 to the 3. So what we need to do first of all is we are given the small f of x, which is e in the power of x. We have to find the capital F of x, which is also f of x, e in the power of x in this case, because if you take the derivative of the capital F, or essentially the derivative of the e in the power of x with respect to the x, it is going to be e in the power of x, which is the small x. So in this case, we're lucky that this function is e in the power of x. So we don't need to make a lot of efforts to find the antiderivative. But essentially, the value of this integration is going to be this capital F at the 3 minus the capital F at the 1. So essentially, it is going to be e in the power of 3 minus e in the power of 1. This is what does the fundamental theorem of calculus part 2 tells us, that we can easily evaluate the integration using so-called antiderivatives. Well, if I put the two parts of this theorem, part 1 and part 2 together, I can clearly see that differentiation and integration as the inverse processes. So let's try to do this for the first part. So I'm going to rewrite this in a different way. So this equation tells you that if you take the derivative of this capital F, you're going to get the small f. But by the definition, the capital F is the integration of this function f of t dt from a to the x. And if you take its derivative, you're going to get simply the f of t, right? Or f of x, sorry. So what does it mean? It means that if you've got some function f of t, if you're going to integrate this first, then if you're going to take its derivative, you're going to get the same function again. Right? This is what does the first part of the fundamental theorem of calculus 1 tells you, that if you've got a function, if you integrate this, then if you take a derivative, you're going to get the same function. So the second part is also going to tell you the similar conclusions. So what we're going to do is, instead of here the small f of x, I'm going to use the f prime of x dx, and I have to integrate this from a to the b. Then this is going to be the f of b minus the f of a, because this f is the antiderivative of this, and antiderivative of the f prime of x is equal to the f. So what does it tell it to you? So it basically tells you that if you've got a function, if you take its derivative, then integrate this, you're going to get the same function again. Right? The first part tells you that if you integrate, then take a derivative, you've got the same function. The second part tells you that if you take a derivative, then integrate this, you're going to get the same function. So these two parts of the fundamental theorem of calculus 1 reveals us the connection between the differentiation and integration. And they are very important theorems, and we are going to use them a lot in this course. Well, I hope that this was very helpful for you and understandable for you. Thank you very much for your attention.